Welcome to part 2 of a Mathematical and Geospatial Technology concept module. It's brought to you by the Geotech Center, a National Science Foundation grant to help community colleges create geospatial technology programs. This is a two-part concept module. The first part includes an introduction to fundamental mathematical principles. The second part is going to use those principles and really look at how a computer works with some specific software use of mathematics and logic. I would suggest viewing part 1 before viewing this part 2. Also, there's a lot of links on the PowerPoint so that you can see more, and I encourage you to go and look at those links for more content. There's also 3 concept modules on statistics, programming, and map projections that may be helpful. This graphic, and we're going to talk about it on the next slide too, is from the Khan Academy. It's really showing the input, the memory, and the CPU, and the output devices of your computer. And what I want you to notice is the little series of zeros and ones that are going from the input devices to the CPU and then out to our peripherals. So here's that same graphic, but really what it's showing is those zeros and ones are flowing between those devices and are all managed by a computer's operating system. So those inputs are machine code of zeros and ones, and it's used by the CPU to execute the operations and produce outputs. This progress includes the use of machine code, assembly language, compilers, and higher level programs, and we'll talk a little bit about those, but the important point is that these zeros and ones represent electrical signals, either on circuits or off circuits, and they're from base 2 numerical systems that are used to generate the machine code. So a computer operating system and applications, that's 2 terms that are used quite frequently. The computer operating system is really the software that manages your computer. So it's the one that works with the keyboard, screens, memory, CPUs, and all the applications. Some examples of an operating system are Microsoft Windows, Apple, Mac OS, and Linux. Applications, or formerly really referred to as computer programs, they interact with the operating system to produce the results to the users. They're normally written in a higher language than the compiled or code language, but we're going to talk a little bit about some of those too. Well, a computer can have more than one CPU. Our little graphic just shows one, but it is the core. It can actually have 2 cores, being dual, or 4 cores, or quads, and most personal computers now have between 2 and 12. Workstations or servers, they may have as many as 48 and could be more in the future. Computer operating systems are not usually written with the machine code, but use higher level programming and scripting languages. And 2 that we hear a lot in geospatial technology are Java and Python. And while it looks more like Common English, both of these computer languages has its own syntax, and that is the rules of how the language is structured, and its own semantics, and that is the meaning of the language, the words that are used in that structure. Well, we've looked at common numeral or numeric systems in part 1. We're going to take a closer look at these number systems, both binary and hex, as they're very important to how computers work. We're used to that decimal number system with base 10, with symbols 0 to 9, and we just know the place values for those numbers. We know that the first digit, say for example of 125, the first digit is the ones, the second digit is the tens, the third digit is the hundreds. But really, if we look at it systematically, when we start on the right, we can see that it is a power of 10. It's 5 times 10 to the 0, plus 2 times 10 to the first power, plus 1 times 10 to the second power, and we can add those together to get our 125. It's a bit different with the base 2, and we're going to look at some of those, but they also have place values by powers of 2. The hex system is the same. They also use those strange symbols, and we're going to take a closer look at how those symbols and what they mean. For example, the number 2,475 in base 10 can be translated to this in base 2. It's a series of ones and zeros and ones, and it's quite long. In base 16, it's much simpler. It's just 2AB. Anyway, you can see more of this and understanding on the rapid tables where you can convert from one to another on the link below. We're going to look at a closer example of the base 2 binary number system. And remember, it's what is used in computers as machine code, and it has two symbols, zeros and one. It's a positional system, just like our decimal system, and each place represents a power of 2. For example, the number 1 in binary code is 0001, and that has 4 places. So the first place where the 1 is 2 to the 0, and any number raised to the power of 0 is 1. The rest of them are 0, 0, 0, so there's no other values. Let's get to a little bit more complex one. How about the number in decimal of 10? In binary code, it's 1010, and it has 4 places or bits. And if we look at those numbers, we see 1010. Well, starting from the right, we have a 1. 2 to the 0 is 1. To the next place value is 2 to the first power, and it has a 1. 2 to the second power is a 0, so there's no value. And 2 to the third power has a 1. When I add those together, 0 plus times 1 is 0, plus 1 times 2 is 2, plus 0 times 4 is 0, plus 1 times 8 is 8. I add those values together and I get back my decimal value. Next, we're going to look at an example from base 16, or the hex number system. And we've seen that base 16 uses those 0 to 9 numbers we recognize, and then it uses symbols that we recognize as letters, but they really represent values from 10 to 16. If we look at the number, the decimal number of 756, in hex it's 2F4. So it has 3 place values, and each is a power of 16. If I start from the right again, I see that the 4 is in the place value of 16 to the 0 power, so 4 times 1. The second place value is an F, which is 15, so it's 15 times 16. And the third place value is 16 to the 2, and I happen to have 2 of those. When I add those values together, 4, 240, and 512, I get 756, or back to my decimal number. I'm going to add some more details about numbering systems and computers. For binary code, it's usually displayed in 8 digits or 8 bits with spaces between the groups, and this is just an example of 2 8-bit word lengths. 8 bits are called a byte, and the largest number that can be expressed in this system is 255, but because we also include 0 in this, we can go from have 256 possible values. Processors or CPUs have what's called a fixed length or number of bits of data in a string that it can handle as one unit, and these are usually called word length. The limit that is specific to a PC architecture is usually shown in multiples of 8, so 8 bits, for example, 8, 16, 32, and so on. 2 of the terms that we often see are single precision and double precision. Single precision has a word length or bit length limit of 32 bits, while double precision has a string length of 64 bits. The word length, though, limitation can be expanded, and we talked about in earlier part 1 about floating points, and it's similar to scientific notation but not restricted to powers of 10. So here we can have in powers of 2, where the number m is raised to some power of 2 to the exponent n. So really the computer speeds and its abilities to handle data and go from input to compute to output devices. A 32-bit computer CPU can theoretically access 2 to the 32nd bytes, or about 4 gigabits, or a billion bytes of random access memory. And it's a very large number. In contrast, a 64-bit computer CPUs can theoretically access, I can't even think of what digits these mean, but you can see the numbers there. It's bytes of RAM, or more than 16 exabytes of memory. So you can see the difference between the 32-bit and the 64-bit. Much, much more accessible RAM. So really, think orders of magnitude. A 64-bit computer compared to the 32-bit computer, it actually has 9 orders of magnitude more of its ability to access random access memory. Also, when you're buying a computer, your speed and stability also depend on your graphics cards and your graphic processing units, and the size of RAM that is accessible to that CPU. And there's a lot of things. I put 2 links on here that can go more into those graphic cards and things. Also, you should be aware that software is developed for specific CPU capabilities, and some 32-bit software may work on your 64-bit CPU, but no 64-bit software should be able to run on a 32-bit computer. This is an example of how base 2 and base 16 number systems are used in geospatial technology applications, and this is just a couple of examples. One of the applications is how your house colors are assigned by each pixel in an image using binary or hex values. And it tells how the device, your monitor or other visualization device or printer, should calculate what the color should look like. Binary representations that we've shown is a usually pretty long series of zeros and ones. And 16-bit just makes it a bit easier to remember and use those same values. So I'm just going to compare a couple of things about the difference between binary and hexadecimal for the same pure colors. Just remember that these systems, we can get 16.7 million unique colors. In binary, the first 8 bits are for red, the second 8 bits are for green, and the last 8 bits are for blue. In hex, the first 2 are for red, the second 2 are for green, and the last 2 are for blue. And we're going to look at an example of the software applications of these. But here you can see the red and the binary in the series of ones and zeros, hex FF0000, green and blue. So here's 2 examples from software applications. One is from ArcGIS, ArcMap from Esri, and the other one from ArcGIS Pro. Generally, software will use a dialog box that allows you to specify what colors you want or how you want those colors mixed. And usually they are in displaying of 8-bit, so 0 to 255 values, and where the values then for the 3 different colors are shown in 3 separate boxes. So the top right one here is the values for red, green, and blue colors, and the software at the top right are all in base 2. So red 255, green 211, and blue 127. Just for example, black would be all zeros for red, green, and blue, and white would be 255 for each of the values. Note though that other channels such as cayenne, magenta, yellow, and black can be used, which has 4 colors, and these are often used for printing. And there are other formats. Bottom right shows an example both with the RGB with the 3 values, but also it gives you your hex values. And in this case, it's FFD37F. So different ways of determining a color. Now we're going to look at something that's not really mathematical per se, but it is related to binary systems in that it's not non-numeric logic operators, but for the logic operators, they're used on binary logic. So 1 if true and 0 if false. These are Boolean logic operators, and they came from a Gita example. And it includes, what the operator is, its function, and what the results are. So there's and, or, XOR, and not. So conjunction result is, for and, is result is true if both selections are true, or is a dysfunction, result is true if either selection is true. XOR is result is true for all arrays that meet the first or the second selection, but not both. And then negation, result is true for all arrays that meet the first but not the second. This is just some examples of Boolean logic. So if you have and you want x to be greater than 6 and y to be less than 8, only if those two things are correct, valid, do you get the operation is true. Or is a similar thing. You can set your parameters and then the operation is either true or false if your values reach those values. XOR is another more complex one. So you set your XOR values and you get true or false. And then not is shown as the last one. These can get fairly complex, and one good example is having a Boolean logic truth table that shows a complex where you have more than one operator and what the outcomes are. And they're really useful aids for geospatial technology analysis. Geospatial technology applications can be expanded by using programming and coding. And you can modify functions of existing applications, such as in ArcGIS Pro, by using other tools such as scripting or employing languages like Python, Java, or R. This topic is really beyond the scope of this basic module, but we do have other modules on programming, both programming and geospatial technology, part 1 and part 2, and we have a model course on Introduction to Geospatial Programming that can help you. This is a review, and it is a fundamental review or refresher, and there are other concept modules that you can look at, but if you have any questions or suggestions, please do contact me. We are going to try to create quizzes for these and award micro-credential badges, so stay tuned. Thank you.